Today I'd like to talk about number 3, the ellipse. This is a follow-on to number 2, the ellipse, which was a follow-on for number 1, the ellipse. I want to think about a small object moving around in the gravitational field of a much larger object. I'm going to think of the kinetic energy minus the potential energy. I'm going to divide the mass of the moving object out. So what I'm going to be looking at is this quantity. Minus minus is plus gm over r. I'll make up a name for this. I'll call it L. This is the total kinetic minus potential energy per unit mass. I'm going to be thinking in polar coordinates, so speed squared is the derivative of the radial coordinate squared plus radial coordinate squared times derivative of theta with respect to t squared minus the potential energy. There's going to be two Euler-Lagrange equations for this. I'm going to do the theta one first because it's easier and will lead to some simplifications in our problem. So I'm going to look at the partial of L with respect to theta. No theta, no theta. Theta dot appears, but theta doesn't by itself. Partial of L with respect to theta is 0. Partial of L with respect to theta dot, no theta dot, no theta dot. 1/2 r squared will be treated as a constant factor. The derivative of theta dot squared with respect to theta dot is 2 theta dot. That will cancel the 1/2 out and give me r squared times theta dot. The Euler-Lagrange equation for the theta variable is easy enough to figure out. Partial of L with respect to theta was 0 though, so I'll just stop writing that down. This says that the derivative with respect to t of r squared theta dot is 0. This means that r squared theta dot itself must be a constant. I'll call that constant h. H is the angular momentum of the moving object divided by its mass. It's the angular momentum per unit mass. This will let me figure out that theta dot, which is d theta dt, is a constant h divided by r squared. That'll be very useful to know in what's coming. The other Euler-Lagrange equation, the one for the r, will be calculated in a similar way, but it's going to be more complicated. Partial of L with respect to r, no r there, 1/2 times 2 times r times theta dot squared, that's going to be r times theta dot squared minus gm over r squared. Partial of L with respect to r dot is 1/2 times 2 times r dot. The Euler-Lagrange equation becomes derivative with respect to time of derivative of r with respect to time minus r theta dot squared minus gm over r squared equals 0. This is second derivative of r minus r theta dot squared minus minus is plus gm over r squared equals 0. Dot here means derivative with respect to time. Putting our formula for theta dot into that last equation, I can get rid of all references to theta dot. Second derivative of r with respect to t minus h squared over r cubed plus gm over r squared must be 0. We're going to modify this in two different ways. Firstly, I'm going to replace all derivatives with respect to t with derivatives with respect to theta instead, and then after that we will change the dependent variable as well. So firstly, r dot, which is dr dt, because of the chain rule, this is dr d theta dt. D theta dt, though, is h over r squared. So r dot is h over r squared times derivative of r with respect to theta. The second derivative of r with respect to t is the derivative of the first derivative of r with respect to t, which I can write as the derivative with respect to theta of h over r squared dr d theta multiplied by d theta dt again. It's the chain rule again. This factor is an additional factor of h over r squared. I'll write that out front. I'll have to use the product rule and the chain rule to get the rest of it. Here I'm going to have h over r squared, the second derivative of r with respect to theta, minus 2h over r cubed times derivative of r with respect to theta times the other derivative of r with respect to theta. The second derivative of r with respect to time is h squared over r to the fourth power. The second derivative of r with respect to theta minus 2h squared over r raised to the fifth power times dr d theta squared. This is that. Next, I'm going to divide through by h squared, which means the h squared goes away in this term, that one, and will show up in the denominator in this last term. Also, I'm going to multiply through by r to the fourth power to try to make the equation look a little nicer. Lastly, I'm going to express r as 1 over u and rewrite my equation in terms of u and theta. Putting all of this together, second derivative of r with respect to theta is this quantity, I'm going to subtract away 2 over r, 2 times u. I'm going to multiply by the square of dr d theta. When I square this, the negative sign goes away. I'll have 1 over u to the 4th power du d theta squared minus r minus 1 over u plus gm over h squared times r squared times 1 over u squared must be 0. After all of this, a miracle happens. This is 2 over u cubed times the square of du d theta that I'm subtracting away, and that is the same as that term, so those terms cancel each other out. Canceling those terms and subtracting the gm over h squared 1 over u squared over to the other side of the equation, multiply through by -1, multiply through by u squared, this is the differential equation for the orbit that we're interested in, written in terms of variables u and theta. U is the reciprocal of the r coordinate. Theta is the ordinary polar coordinate angle. Coming up next, solving this equation.